Welcome to the deep dive. Today we're exploring a really fundamental pivot in multimodal understanding. We're talking about shifting visual representation away from raw appearance and towards something more like an executable blueprint. If you've been tracking the progress of advanced AI agents, you know code is just crucial for reasoning and action. But historically, AI's success with code has been mostly focused on linguistic tasks, programming or debugging.
And that's the core challenge here. Conventional image representations, they rely on these dense RGB pixels. A dense pixel array captures visual appearance perfectly. All the subtle shading, the color.
It's high fidelity.
High fidelity, but very low on structure. It gives you a lot of information, but not much abstraction to reason with.
So if pixels are high fidelity, what's the alternative? What gives you that high structure? The researchers here are proposing scalable vector graphics, or SVG code.
Right. SVG code is what they're pushing for because it's compact, it's easily interpretable, and most importantly for these agents, it's executable. It represents the visual world the way a human might draw a sparse symbolic sketch.
So it's emphasizing edges, spatial relationships, object outlines, not millions of color points.
And this shift really materializes in the creation of VCode. It's a benchmark that reframes the whole idea of multimodal understanding as a code generation task. The model sees an image and has to output SVG code.
And that code has to preserve the symbolic meaning for any later reasoning. So that's our mission today, to see how current frontier models handle this job of turning a photograph into a blueprint.
Let's really drill down on this symbolic shift. We know pixels capture dense visual appearance, but an SVG being a vector representation, it's all about geometry and relationships. Can you paint a clearer picture of the operational benefit for an agent?
Sure. Think about the difference between a photograph and, say, a CAD drawing. The photograph is your pixel representation. If an agent wants to move a chair in that photograph, it has to recalculate and render millions of pixels around the object and its new location. It's a huge computational load.
Right. An SVG, though,
Yeah.
it only deals with coordinates and paths. So if an agent wants to move the chair, it just modifies the coordinate values in the code for the object named chair.
It can just edit a few tokens.
And that's the definition of executable reasoning. This abstraction emphasizes these sparse symbolic elements, how things relate to each other, how many there are, making it a perfect intermediate layer for planning.
That makes the benefit so much clearer. The source materials use this great example of an image with 3 sheep on the farm.
Yeah.
The dense RGB image gets translated into this compact SVG code. And when you render it back, the SVG isn't photorealistic at all, but it absolutely retains the symbolic meaning. You can still count 3 sheep in the right setting.
You're losing appearance, but you're gaining actionability. And that's the trade-off.
And SVGs aren't new, right? They've been used for logos and icons for ages.
Right, but that's for synthetic assets. VCode is really pioneering their use for representing and reasoning over these complex, natural, real-world images. It's asking models to abstract reality, not just simple diagrams.
Okay, so to really test this abstraction capability, the VCode benchmark had to be extremely diverse. How did the researchers make sure the difficulty was high enough to challenge these frontier models?
Well, they repurposed existing large multimodal benchmarks, but they did it very selectively. They wanted to cover 3 distinct and challenging domains to get diversity in both the taxonomy and the difficulty.
Okay.
So the first domain is general common sense. This was adopted from MMVet, which gives us about 218 image question pairs. This is your everyday knowledge about objects and how they interact.
Standard stuff.
Then they raise the stakes. The second domain is professional disciplines and college-level knowledge. This segment pulls specialized subsets from the MMMU benchmark.
So what kind of knowledge are we talking about here? When you say college level, what does that actually mean?
It often involves really complex diagrams, charts, or images that need specialized domain reasoning. So like identifying components in an engineering blueprint or understanding a biological process flow. That part added another 146 pairs.
And the third?
The third is the most visually demanding. They call it visual-centric perception, and it's drawn from CVBench. This one targets concepts that are really hard to encode in 2D vector code. Things like object counting, relative distance, and the extremely tricky concept of 3D depth.
Yeah, encoding 3D depth into a 2D SVG, that sounds like a serious abstraction challenge. So altogether, that gives us 464 image question pairs.
Yeah.
But the crucial part, you said, is the evaluation protocol, CodeVQA.
Right.
How does that protocol guarantee that the model preserved the symbolic meaning and not just some rough appearance?
CodeVQA is brilliant because it makes the SVG executable. It forces a second vision language model, they call it the policy model, to answer questions about the original image by reasoning only over the rendered SVG.
So the test isn't, did the first model make pretty code? It's, does the rendered code contain enough structural truth for a second model to get the right answer?
That's the idea. If the abstract, lossy SVG can guide the policy model to the correct answer, that shows faithful symbolic preservation. If it loses critical information like it forgets to include one of the three sheep, then the downstream reasoning will fail.
Makes sense. Are there other metrics?
Yeah, they used two secondary ones. One was the SIGLIP score. This is a measure of semantic content preservation. It's basically checking if the embedding space of the original image is consistent with the rendered SVG's embedding space.
To make sure the meaning hasn't drifted.
Right. And the other metric was just code token length. It's a proxy for efficiency, the idea being that a good coder should be concise, right? Use minimal tokens for maximum fidelity.
Okay, so moving into the results. The sources really highlight a persistent struggle. These frontier VLMs have a tough time generating faithful SVGs from natural images. Before we get to their solution, what's behind this struggle? Why is visual coding so much harder than text coding?
It's a mix of scale and, well, blindness. First, code for a complex scene can easily run into thousands of tokens. VLMs often struggle to maintain context and coherence over such long code inputs.
And the blindness?
The output is visually blind until you execute it. When a VLM writes a line of text, it can sort of predict the linguistic consequences. But when it writes a line of SVG code, it has to anticipate the exact pixel consequences of that geometry without seeing it rendered.
It's like programming in the dark. That's a really tough problem. So to bridge that gap, the researchers introduced VCoder. It's an agentic framework. What does it do?
VCoder augments existing coders with two main capabilities. It's about introducing feedback and structured perception. The first one they call thinking with revision.
Okay, that sounds like self-debugging, but for vision. How does that revision process work?
It's a feedback loop. The model generates an intermediate SVG, it renders it, and then it compares that rendered image back to the original raw image.
Okay.
And it has to explicitly articulate the discrepancies, comment on the difference, and then use that feedback to refine the SVG code. It's an internal self-correction based on visual verification.
And did that actually work? Did they see gains just from forcing the model to reflect on its own output?
They did. The results show that even just one revision round gave tangible improvements in the CodeVQA scores for models like Claude and GLM 4.5v. It proves that visual self-correction helps a lot.
So what's the second capability? You said it addresses the VLM's blind spots.
The second one is acting with visual tools. This is all about externalizing specialized perception. They equip the coder with dedicated toolboxes to provide structured cues that go beyond what the VLM can do on its own.
So what kind of tools are we talking about?
They use three specific ones. First, for category and location, they use object detectors like Florence 2. This provides semantic labels, this is a bird, along with the bounding box coordinates.
So it turns fuzzy concepts into hard data for the SVG.
It does. Then for capturing complex boundaries, because, natural objects are rarely perfect squares. For shape, they use SAM2, which generates detailed segmentation masks. And critically, these masks are then simplified into polygonal paths. This is essential for encoding irregular boundaries, like the outline of a tree, directly into SVG path elements.
Then the last tool was for text, I imagine.
For text, yes. They used OpenOCR to detect and transcribe text regions, and then they encode them directly into the SVG using the text tag. This stops critical information, like a sign or a label on a diagram, from getting lost.
This combination of tools sounds like a huge advantage. What did the ablation studies show about their impact?
The impact was really profound. The ablation showed that the full visual tool ensemble gave a 16.6-point improvement over the Claude 4 Opus baseline. It wasn't just a small bump. It was transformative.
Wow.
And they also noted that the shape cues from SAM2 were especially helpful for improving spatial reasoning. It just underscores how vital accurate boundary encoding is for this kind of symbolic representation.
So let's synthesize the big performance findings. What was the headline score improvement for VCoder?
VCoder, which was built on Claude 4 Opus, delivered a pretty significant overall gain. It lifted the CodeVQA score from 41.7% to 54.0%. That's a 12.3% gain just by integrating this framework in its tools.
That's substantial. And what about the models themselves? Was there a link between general reasoning ability and this specific visual coding task?
A very strong one. They observed a strong correlation. The closed-source models, which are typically seen as having superior general reasoning, perform better at visual coding.
So GPT-5, for instance, set the highest baseline score at 46.8%. This suggests visual coding isn't just about parsing pixels, it requires some sophisticated semantic understanding.
It does. But here's the tension. Even with the best models, the benchmark is still incredibly difficult. The raw image upper bound, that's the score you get reasoning over the original photos, is 61.7%.
And GPT-5's 46.8% is still a long way from that.
A long way. It concerns the benchmark is challenging, and there's a lot of room for improvement in symbolic representation.
Where do the models struggle the most? What was hardest to translate into SVG?
Two areas really stood out. Within that common sense domain, the knowledge dimension from MMVet was consistently the lowest scoring area for all the models. And in the perception domain, scores were lowest on 3D relations.
Things like depth and spatial position.
Yeah, concepts like depth order or relative spatial position. Encoding those into a 2D SVG is proving to be a really persistent headache.
And what about code length? You mentioned it was a metric. Was the hypothesis correct that shorter code is better?
Well, the data actually complicated that idea. They found that models producing very short SVGs, maybe around 300 tokens, generally underperformed compared to stronger models that were putting out much longer sequences.
Sometimes over 2,000 tokens.
Yeah. So performance seems to scale with the usable context length.
So complex scenes just demand longer, more detailed code. You can't capture a highly structured image with just a few lines.
That seems to be the case. And the ability to manage that long sequence is crucial. And there was one other key insight about modality, the approach they called MG2Text2SVG.
Where they first describe the image with language.
Right, where you first translate the image into a detailed caption before generating the code. That approach achieved better performance than the direct MG2SVG approach.
That's a really interesting finding. Language seems to be a necessary intermediate step. Why do you think adding that linguistic step helps the model abstract better?
Well, the language generation step forces the VLM to parse and structure the scene's content semantically first, before it tries to encode it visually. It's almost like writing an outline before you write the code.
It reduces the blindness?
That's likely it. This pre-structured parsing probably reduces the inherent blindness of direct visual-to-code translation, and that leads to a more faithful symbolic output.
This research also included a human study, which brings us to a compelling final observation about alignment. How did humans do when they had to reason over these abstract SVGs instead of the raw images?
The findings were strikingly consistent with the VLM results. Humans also performed significantly worse when reasoning over the rendered SVGs. The human score dropped from about 50% when viewing raw images to just over 40% with the SVGs.
That's a big drop, and that consistency between human and VLM performance is really the concluding insight here. Both of us, human and machine, seem to struggle in a comparable way when information is lost through this kind of abstraction.
It suggests a sort of shared mechanism. Despite the information loss, the ability to reason from these high-level, sparse symbolic representations, these executable blueprints, it appears comparable between us and these advanced systems. The benchmark really confirms that symbolic abstraction is a key mechanism for advanced understanding.
The consistent performance drop across both humans and VLMs suggests that the limits of abstraction might be fundamentally the same for biological and artificial intelligence. So the final thought for you to consider is this. If the goal is truly effective agent reasoning, maybe the path forward depends less on trying to achieve perfect pixel fidelity and more on the ability to distill the world into these shared executable blueprints that both humans and AI agents can process effectively.